So relation between field and potential. Relation between field and potential. In this case, we will take, say, two equipotential surfaces. Okay, let's say this is an equipotential surface, and we take another equipotential surface. These are two equipotential surfaces, one surface over the other. Able to understand? Okay. And so this is a equipotential surface, and this is also equipotential, but their potentials are different. Their potentials are different. This is one surface. In this surface, it is equipotential. Means what? In this surface, if there are 2 points, potential is same. In this surface, if there are 2 points, potential is same, right? So we take a point. Let's say we have a point A out here, and on the other one we have a point B. Say B is another point, right? A is 1 point and B is 1 point, and there will be this electric field. So let's say the electric field is in this direction. Electric field is coming perpendicular to one surface, another surface. Are you understanding? This is like, imagine you've got like, say, shell columns. One column, one another concentric column. You have taken two parts of the shell. The electric field will be coming from the center. It's a cylinder, parts of cylinder. This is one cylindrical pipe, this is another cylindrical pipe, right? So this is the electric field. Sorry. Say this is the electric field E, right? And this is the electric field E, and we have a small length element from here to here. The length element is del L. Say del L is the length element. Okay. Now there will be some conceptual issues with us. The book says that the potential here is V, right? The potential here is V, and the potential, and let's say we have a point charge. There will also be, let's say, okay, consider two equipotential surfaces A and B, and imagine that a unit positive charge is moved along the perpendicular from the surface B to the surface A. From B to A, you are moving a point charge, right? From B to A, I am moving a point charge. Electric field is in this direction. So what is your idea about the potential that will develop? Whose potential should be more? You are moving it from B to A, right? And the electric field is in this direction. Imagine the spring. Are you compressing the spring or elongating the spring? Compressing the spring, because the electric field is in this direction. The force is in this direction. Electrostatic force is in this direction. There is some charge here, and you're moving a charge from B to A. So what am I doing? I am compressing. So if I am compressing, whose potential should be more? Point A or point B? You're moving it from B to A. Point A should be more. Now listen, the book is saying that the potential at A is taken as V, and the potential at B is taken as V plus del V. Now this is not that NCERT is wrong. This is what we have to understand, right? Just understand. So we say A and B are equipotential surfaces, right? E is the electric field radially outwards, and bracket you can say normal to the surfaces. Children, is this much clear or not? Surfaces, okay? Delta L is the del L is the perpendicular distance between A and B surface. Till here, correct? Okay. Unit positive charge. What do you understand by unit positive charge? Plus 1 coulomb. Plus 1 coulomb. Unit positive charge. Okay, whenever we take unit positive charge, we'll always talk about potential, because potential is potential energy per unit charge. Work done per unit charge. But whenever we define potential energy, we will always take test charge. Okay. Unit positive charge is moved from B to A. B to A. Now, what is your analogy? Our analogy should be that the potential at A must be more than the potential at B. Has to be, because the energy will be more. Yes or no? Right. But let's see what NCERT is taking. NCERT analogy. NCERT says that at A, the potential is VA, right? At B, the potential is VA plus delta V. As a difference has been created, right, between our analogy and we are both correct. We are to 100% correct. Now, if you want the NCERT analogy to fit, then you will accept this only if mathematically you find that delta V is negative. Because if delta V becomes negative, then this statement holds true. VA minus something, so less than VA. यही story है, ठीक है ना? यही story है. Many children, while reading this, the first thing they will say, let the potential at V be equal to VA, let the potential, let this be equal to V, and let this be equal to V plus delta V. Sorry, I just mentioned it as VV. It is V, and this is V plus delta V, right? There is where the concept difference arises between NCERT and our NCERT. But as I told you, beta, there is nothing wrong in the way you are conceptualizing the system. It is absolutely correct, and NCERT wants to stick to that. Their analogy is also correct, and we will try to now see how both the analogy remains correct, and both the analogy remains correct only if delta V is found to be negative. Is this correct? Okay. Now, let's see the work done. Work done. What is the work done? Work done in moving. Work done in moving what? Work done in moving that charge, unit positive charge, from this point to this point. Let's go to our basic. What did you understand about voltage is equal to work done divided by charge? Correct? Work done divided by charge. Okay. The work done is also equal to the force multiplied by the displacement. The force multiplied by the displacement. What is the displacement, beta? The displacement that you are doing is nothing but delta L. The force multiplied by delta L. What is the force? The force is nothing but Q multiplied by E into delta L. Is this understood? All these are clear. So now we go by our book. The work equals to the potential difference between A and B. So we will write the work done, W external, should be equal to the potential difference between A minus VB. Potential energy of A minus potential energy of B. So what is the external work done? The external work done is given by E. Now, when we take work done, we are taking only the modulus of E. We are taking the modulus of E, E vectors modulus, just the modulus, because work done is a scalar quantity. Now look, work done is E into Q. But what sort of Q are you moving from here to there? Unit positive charge. So no point in writing Q. Q's value is equal to 1. So E delta L, right, should be equal to, what is the value of VA? V. And what is the value of VB? V plus delta V. Delta V. So what do you get the value of E from here? The value of E that you get is negative delta V by delta L. आ गया ना negative? ठीक है? Just write this much. If you have understood this, just write this much. External work done is VA minus VB. Ultimately potential, final potential minus initial potential. Okay. From here we understand one thing, that the electric field, you are trying to find out what better relation between electric field and potential. The electric field direction is always along the direction of reducing potential. Reducing potential. By this definition, we have found that delta V will become negative. So if the potential reduces from where? From here to here, the potential reduces. Electric field will be always in the direction of reducing potential. Now, what is the magnitude of the electric field potential? See, the magnitude of the electric field potential. What is the magnitude of this electric field potential? It is the change in potential per unit displacement in a direction perpendicular to the direction of the equipotential surface or along the direction of the electric field. So it lies very nicely. Is the magnitude given by the change in potential per unit displacement. So we write it as, acha, is electric field is never positive or negative. In electric field, it is always positive. So what is the electric field magnitude? Say suppose you want to find out the electric field here and the electric field here. The electric field here will be given by how much potential drop happened divided by the length of the perpendicular between the two surfaces. At that time, ये negative हम नहीं सोचते हैं. Is this getting clear? Electric field is neither negative or positive. That's because of the direction. The magnitude of electric field is never. What is electric field? Electric field is force per unit charge, Newton per coulomb. You never say it as positive or negative. So when you define electric field magnitude, we define it as, it is the magnitude of change in potential per unit displacement in a direction normal to the equipotential surface. Software is causing some problem, okay? Equipotential surface. Try to understand once again, right from start. Electric field magnitude. Magnitude means, though we have shown magnitude as negative dV by dV, but if when you calculate electric field magnitude, you can actually calculate it as simply dV by the magnitude of this divided by dA. Acha, bacha, have you understood this or not? Let us see it once again. Have you written? Okay, let's see this. Okay, let's see this. This will be very useful definition and formula. We have two equipotential surfaces A and B such that the electric field is in the direction outwards, normal to the surface, pointing from A to B. The electric field is upwards, right? You are bringing a positive charge. From where? From B you want to move it to A. So if you are moving it from B to A, you are moving it against the electric field. That means you are compressing a spring. So when you bring it to A, the charge is more energized. So the potential at A should be more than the potential at B, right? But when we go by the NCERT definition, then what they are saying is that they have taken the potential at A as V and the potential at B as V plus delta V. Our heart says this should be V and this should be V plus delta V. NCERT says no, this is delta V. There's a reason for that. They are showing it because they will prove that delta V is negative. It's a negative gradient. It's a negative gradient. Means the more, what do you mean by gradient? Gradient is this. The more you go, the voltage reduces further. It's a negative gradient. Like, how do I tell you? Like say, the rate of interest. If you want to earn from the bank, then the derivative of that interest will be positive. Principal over time, say dp by dt is positive. That means every year passes, money gets added to your account. But suppose there is a negative rate of interest out here. So there the dv by the rate of interest is negative. So our population growth is negative. So our dp by dt is negative. Every year the population will come down. There is no more growth in it. The population is negative. Here also they are going to find out there is a potential gradient with respect to displacement. Is it a positive gradient that you found out? No, it's a negative gradient. So NCERT is also, their assumption is correct because they have found out that the finding is actually correct. It's a negative gradient. The more you are going on top, the voltage is reducing further and further, which was our concept also. And we said that aap isko V rakho, isko V plus delta V rakho. They said this is V plus delta V. Now you are moving a charge. What is the external work done? The external work done is VA minus VB. No doubt about that. What is VA? V. And VB is V plus delta V. So finally you are getting a negative. So the electric field you are finding, the magnitude of electric field is a negative gradient. It gives us two ideas. One is electric field will always be in the direction where reducing, in the direction of reducing potential. Whenever potential reduces, electric field will be in that direction. Number one. A lot of questions come on this one. Second thing that we understood is that the electric field magnitude is given by the potential difference. You just take the magnitude. Ab negative positive se kuch nahi lena dena. Just take the magnitude and divide it by the perpendicular length between the two surfaces. So the electric field will keep on, you get the value of the electric field at this point. If you actually see this definition, it is not that you have invented something new. See, basically what did you get? You tried to find out that an electric field is delta V by delta L. Can I write just like this as V over L? ऐसा लिख सकते हैं. This is what you tried to find out. What is the definition of electrical field, beta? K Q divided by KQ means the field due to a source charge. This definition is KQ divided by R square. Is this the definition of electric field? Yes. No, sir. Write it more this way, then only I become clear. Okay. This is the definition of electric field. What is this? Potential. What is potential? L can be considered as another R. Bring another R. Match again. Same definition. Potential divided by this is same as electric field. Dimension wise they are same. You did not invent anything new. Is this understood what I tried to say? So there will be some questions based on this where the length of separation between two surfaces will be given to you and the voltage difference will be given to you. You need to calculate what is the electric field out here. So is this clear? Have we understood? Right. So our next topic is potential energy due to a system of charges. Now you will say, sir, this we had learned. No, you learned potential due to a system of charges. Now what are you learning? Potential energy due to a system of charges. And whenever potential energy comes, your charge changes from test charge to, for unit positive, to a test charge. Okay. Say, it says, consider a simple case of two charges Q1 and Q2. So let's say this is a charge Q1 and this is a charge Q2. These are two charges, right? And position vector are R1. R1 is a position vector and R2 is a position vector with respect to some origin O. With respect to some origin O. Means, if you want to make it more elaborate, there is some origin, something like this. With respect to some origin, R1 and R2 are two position vectors of two charges Q1 and Q2. Okay. Our job will be, you're trying to find out what is the potential energy due to a system of charges. Now this is your system of charges, where the system of charges has got how many charge? Two charge. You want to now build this system. I want to build this system, and in order to build this system, I will see what is the energy buildup. That is nothing but the potential energy due to system of charge. I'll build up this system. It says, let us calculate the work done externally in building up this configuration. We will see what is the work done. So this means we consider the charges Q1 and Q2 initially at infinity. So Q1 and Q2 are both initially at infinity, because you want to find out what is the potential energy. So you will move them from infinity. Okay. Now just see. So we go to infinity. We go to infinity, and in infinity we have kept both Q1 and Q2. Please understand. At infinity we have taken Q1 and Q2. Okay. Now the first charge Q1 is now transferred and brought. The first charge is being brought from, say, Q1 to a point R1. Q1 is actually brought. Q1 has been brought from infinity to R1. Right? Q1 has been brought from infinity to the point R1. What is the point R1? This is the point R1 where you have brought. R1 means it is at a distance R1 from the origin. Okay. Q1 from R1. Now when you are bringing Q1, try to understand, when you are bringing Q1 to R1, there was no charge out there present at all. There was no charge. This is the configuration we will create. How we are creating, I am trying to do that. Right. And if you still have a doubt, the doubt is something like this, that sir, what is that R1? That R1 is this one. This is actually that R1 vector. So this point is taken as R1. You have brought it till R1. When you brought it till R1, at that time, bacha, there was no charge in this region. So the work done by you is actually 0. No charge was there. No charge there means you will not do any work to bring it. Right? So initially, Q1, Q2 are at infinity. Okay. Q1 is moved till R1. W external is equal to 0, as no charge pre-existed. Our system is because of two charges Q1 and Q2. हमने तो सिर्फ Q1 को लाया and no charge pre-existed, so the work done is equal to 0. Right? Now since the charge has come here, right? Consider another one point just consider one point, arbitrary point. Let's say this is one point P, and this point is R1, position vector is R1. Okay, but consider one point P. So what happens? This produces a potential, and this potential is given by at P you will get a potential V1. Now V1 is due to Q1. What is this potential equal to? Q by 4 pi epsilon naught R1P. Acha, have you understood what we have done so far? Once again, don't concentrate on this. This is what we will build up. We take two charges in infinity, and there is no charge pre-existing. This is my origin. From origin, there is a point R1. There's a point R1, which is connected by a vector R1 vector. You are moving a charge from infinity to R1. Was there any charge pre-existing here? No. That means your work done will be equal to 0. This is equipotential type. Now, since you have brought Q1 here, any point, arbitrary point P, and what is this distance? This distance is R1P, between R1 and P. There is a potential which you will feel due to Q1. Do you agree or not? What is the potential at a point due to a charge? Q by 4 pi epsilon 0 R. This R is R1P. Right? What should happen next? We have to build this system. So we will now bring another charge. So Q1 has come, Q2 also has to come. Q2 will now encounter a potential. Because now when Q2 is being moved, one charge is already existing out here. So work will be done, right? So we go by R1 by P at a position. Now, from the definition of potential, work done in bringing the charge Q2 from infinity to a point R2. Okay. Now let's have another point. Let's have another point. Say this is our another point, which is R2. So this is R2 vector, and this point is called R2. Okay. Now you are going to shift whom? You are going to shift Q2 to R2. So let's shift Q2 to R2. So we are shifting Q2 to R2. All right. This is Q2. We are shifting Q2 to R2. But when Q2 is coming towards R2, there is already a charge Q1 in his vicinity, right? And that charge has a potential energy in and around it. So Q2, when it comes, it will face the impact of that potential already. So it says that from definition of potential, work done in bringing. So what is the definition of potential? V is equal to W over Q. Do you agree? So W is always equal to V into Q. So the work done in bringing the other charge should be equal to the existing potential multiplied by the charge. Work done in bringing what, beta? Work done in bringing Q2 from where? From infinity to where the point R2 should be equal to the potential which is existing at that place. Say that potential is some V1. आपने इस point को P लिया, इसको ले लो, एक ही बात है. The potential at this point multiplied by the charge Q2. Do you agree or not? So we say that the work done on Q2, this will be equal to 1 by 4 pi epsilon 0, which is obviously Q1, and now it will be R12. Acha child, what is R12? R12 is this. This was just an arbitrary explanation. Any point you take, okay, make your diagram, then I'll explain. Make it. Make the diagram, and once you're done, you let me know. Okay, so let's understand it. We are going to find out what is the potential energy due to a system of charges. That means our system will have two charges, and what is the potential energy of such a system? That is what we are going to find out. That means the system will look like this, that there will be a charge q1 at some distance position vector r1. There will be another charge q2 at some position vector r2 with respect to a origin of a system. What is the energy of this system? We have to find out. What is the total value of this system, monetary value? So we start from scratch. We say that this sort of system does not exist. We will create this system. So we have q1 and q2 which are placed at infinity, and we locate a point r1. In this r1 point, r1 is how? Similarly, like that origin where you want to find out that is at a distance r1, that is some point in space. You want to bring q1 from infinity to r1. Was there any charge pre-existing here? No, there was no charge. So the work done in bringing q1 from infinity to this is zero. You spend no work, right? This is the first person who inhabited the island. Did you need any permission to inhabit that? No. But once one person has inhabited, the next person will definitely seek an approval. Who is the next person? Q2. Okay. Before bringing q2, let us understand. Now that q1 has come and sat on this island, there are various points where you will feel the presence of q1. And that presence is felt by the potential due to this point. We have studied in first or second class that if there is a charge, any point which is at a distance r, the potential is q by 4 pi epsilon 0 and this particular distance r. So P is not a fixed point. There are innumerous such points P now in this island, where wherever you go, you will feel his presence because he has already occupied the island. So and then you can ask, sir, if I come and occupy this space in the island, how much potential will I feel? R1P. Sir, if I would have been here at some point S, then how much will I feel? R1S. You will feel some potential. So you're now aware that you are going to go to an island which is preoccupied. You say, okay, let us go to a point R2. Let us go to a point R2. Very good. Will you feel a potential at R2? Definitely. What should be the value of the potential? The initial person who already came divided by 4 pi epsilon 0 minus the vector between you and the position of that person. You did not come and sit at P. You sat where? You sat at R2. Therefore, you say that the work done is equal to, work done is what? Work done is always equal to the potential into the potential value is how much? Q1 4 pi epsilon 0 R12 multiplied by Q2. Is this understood now? Clear now? This is the work done for you to come from infinity to that position, right? Now, tell me one more thing. You did all this work against what type of force? You have done this work. You did this work against what type of force? Electrostatic force. Electrostatic force is conservative? Yes. That means which path you took does not matter. The forces are conserved, so the work done is also conserved. Your external work is now conserved as what? Potential energy of the system. What is your external work, beta? 1 by 4 pi epsilon 0 q1 q2 by r12. This is your work. This work is conservative. We have already learned, because this work is done against electrostatic force. Electrostatic force is a conservative force. This is a conservative work. A conservative work does not depend on the initial and final position, but a conservative work depends upon does not depend on initial and final position. It only depends upon, does not depend upon the path taken. It only depends upon the initial and final position. Such work is completely conserved. That means whatever external work you did, this work was actually conserved and got stored as the potential energy of the system, which is given by 1 by 4 pi epsilon 0 Q1 Q2 divided by R12. R12. Mind you, I have been very biased in this derivation. What does the system? It says system of charges. How many charges did I take? Only 2 to make it easy. We have to now increase the number of charges. Achha, now another question. So if I would have brought Q2 first, you bring Q2 first. So Q2 is the first person who inhabited the island. At any point, what will be the voltage equal to? The voltage will be, sorry, one definition went wrong here. This should be Q1. Okay. What should be the voltage at any point? I will write the voltage is V2 at that time. Q2 divided by 4 pi epsilon 0 and R2P. And then I bring Q1. Then also, do you think this will change? It will not change. Q2 was there, you now multiply Q1. So it doesn't matter whether you brought Q1 first or you brought Q2 first. This will be the expression for a system of 2 charges. Okay. Now it says the potential energy expressed is unaltered by the way the charges are brought, is true for any sign of Q1 and Q2. Now, if Q1, Q2, this is potential energy. If Q1, Q2 becomes greater than 0, if Q1, Q2 becomes greater than 0, this product, that means what? Q1 and Q2 were of the same sign. Then only if you multiply them, they will be greater than 0. In that case, potential energy is positive. Obviously, you brought one charge positive, you have moved another positive charge, so you have energized the system. And if Q1, Q2 is negative, then you have not worked anything. In fact, in that case, if you withdraw one charge away, you are doing work on the system. Because imagine if Q1 was negative, Q2 was positive, then to bring it, you need not do any work. But if you move it, then you are doing work on the system. Then this work will become positive. Okay. Now we are going to generalize this concept. Our next topic would be the same thing. We are going to do what? We are going to generalize for any number of point charges. Now we are going to generalize. We're going to generalize for any number of point charges. So we take now 3 charges, Q1, Q2 and Q3, and we will see what is the potential energy buildup due to these 3 charges. So we have Q1, Q2, Q3, and this Q1, Q2, Q3 are located at R1 vector, R2 vector and R3 vector. These are the position vectors. So children, your setup is now something like this. Your setup is, you've got 3 position vectors now. Right? Let's say this is a position vector R1. This point is R1. We have Q1 here. This is R2 position vector. This is R2. We have Q2 out here. Okay. And this is position vector R3. Point is R3. And you have Q3 out. This is the system you're trying to conceptualize now. Right? R3. So again, first Q1, Q2, Q3, all these will be where at infinity. Placed at infinity. Whom will you bring first? Q1. first shift, and you're going to shift it to where? You're going to shift it to R1. What is the work done? 0. देखो आपको अपने आप समझ में आ रहा है. The work done by you is 0. You are doing 0 work done, and next you bring, and the next one you will be the second shift. The second shift is for to R2, and whom are you shifting? You are shifting, 1 minute, one thing wrong happened. The arrow went wrong. Are there? Okay. Q2 is my second shift to the point R2, and then we have some external work done. This we have already seen. This work done will be given by Q1 Q2 divided by 4 pi epsilon 0. This is R12. This is what we have studied. Okay. Now a little bit of generalization. Okay. This concept is understood? Okay. Now what should be the conceptual for, then if Q3 comes, Q3 will come to R3, and the external work done for Q3 should be equal to Q1, Q2, Q3. This particular voltage multiplied, this is the voltage at 2 into this, right? So we'll do it a little bit generalizing. That is the same concept out here. So generalizing, we say if Q1 would have come to a point P, then it creates a voltage V1, which is given by Q1 4 pi epsilon naught R1P. Do you agree? Right? R1P. And if you would have, since you have brought Q2, okay, Q1 was brought where? Q1 was brought to R1. You are trying to measure the voltage at point P, any point, any arbitrary point P. Is this getting clear? This one, this is a slight difference from here. This is the potential which was there at R2. This is what we studied previously. Here what we are saying, Q1 has come to R1. Q1 has come to R1. You are trying to measure what is the potential at a point P, So the potential at a point P is given by this, right? You have now brought Q2 at R2. You have brought it. Now you are trying to find out what is the potential at P. Once Q2 has come, then Q2 creates a potential at P, which is given by 4 pi epsilon naught R2P, means individually for only Q2. So if I say what is the potential at P due to both 1 and 2, this will be given by 1 by 4 pi epsilon naught Q1 by R1P plus Q2 by R2P. Is it absorbed or not? Just check. Check what we are doing. But Q1 has already come to R1. Q2 has already come to R2. Then we see some arbitrary point P. At an arbitrary point P, if you just think about Q1, what is the potential? Yeah, the potential will be, if you just see the potential at this arbitrary point, then this distance, there is another distance here also, okay? Then this distance is how much? R1P. How much is this? R2P. At P, just due to Q1, the potential is Q1 4 pi epsilon 0 by R1P. Just due to Q2, it is Q2 4 by epsilon 0 R2P, correct? Due to both, what is the potential? Now you are bringing Q3 has already come. Now Q3 is coming. Now Q3 finds this potential already pre-existing at that point, right? So we say the total work in assembling. Now what we do, work done in bringing Q3 from infinity to R3. So work done to bring Q3 from infinity to R3. We are bringing Q3 from infinity to R3. That is the external work done. This should be equal to Q3 times the potential that is existing. Remember I hope this is clear with you. Potential is always work done by charge. Therefore, work done is charge times potential. Work done in bringing Q3 is Q3 times the potential that is existing out here. Yes or no? So we say the work done is Q3 times the potential that is existing out here. So we write this as Q3 into the potential, Q3 into the potential at 1 and 2, due to 1 and 2 at R3. This is not multiplication, this is just a function. How to read it? The work done in bringing Q3 from infinity to R3 is equal to the charge Q3 multiplied by the potential V1 and V2 created at R3. Now, what is the potential V1 and V2 at a point P? At a point P, it is R1P plus R2P. So, at a point R3, it should be R13 plus R23. ये चीज समझ में आया?
So this is R3.
No.
PS.
Yeah, P as R3. See, it's like this. This one you understood, right? Just observe here. If you bring a charge Q1 and you brought a charge Q2, you think of some common point P. What is the net potential at P? The potential due to this and the potential due to this. Very easy. You have added this R1P, R2P. Now you are bringing a charge to R3. If you bring a charge to R3, you are doing some external work. Work done is always charge times potential at that point. Work done in bringing a charge from infinity to this point is charge into the potential of this point. So what charge are you bringing? Q3. Potential of this point. What is this point? R3. What is the potential? If there is a potential at P, there is a potential here also, na? Due to these two. So what is the potential here? The potential here will be given by the potential due to 1 and 2 at a point 3. This is not multiplication. This is at a point 3. Now potential at a point. Now how to find this expression? You already know as a generic expression, potential at a point P is given by, due to two charges, is given by this. So potential at R3 should be given by R13 plus R23. Yes. Yeah, we lost some recording. We should not use this as paperweight. Anyways, the configuration we got now is this. Look at the configuration. The configuration is Q1, Q2, Q3. This is your configuration finally. Right? This is R12. Look here. The R12, R23, R13. This is R12, R23, R13. The configuration, if you see, of energy depends upon at final. See, what is potential energy? Potential energy is due to position or due to constraint. This is the constraint that you created, and the constraint is responsible. How you achieve this constraint is nowhere here in this expression. See, do you have any distance that you moved here in this expression? No. And just imagine, you take a network of many rubber bands together and you stretch it. It has energy now. This energy is due to the constraint. how you created the constraint has nothing to do. I stretched a rubber band from here to here, Neha stretched from here to here, but finally it is here. Now if I release this point, the amount of impact it will do is same as the amount of impact it will do for you also. It's all due to a constraint. So potential energy of a system is always due to the position or the orientation. It has nothing to do by how you achieve this orientation. So once again it says that the work is conservative. It is not dependent on the path. It is only dependent on the final position. Is that understood? Okay. So there is one problem 2.4. Okay, we'll take it up in the next class. And now then we will see what all we have seen now. We have seen potential energy due to a charge, potential due to a charge, potential energy due to a system of charge. Now we will see potential energy versus electric field. We saw electric field due to voltage. That is also we have seen. Our next topic will be potential energy in an external field. Suppose there is an external field running. Now there is no external field here. Suppose there was another external field. Then what is the potential energy? Okay. So we'll close it here.